Hello, this one it is the Coulomb's law, and according to that Coulomb's law, it states that the force between two point charges Q1 and Q2 is directly proportional to the product of the two charges and is inversely proportional to the square of the distance between the two charges. Here it is the charges Q1 and Q2, and this R it is the distance between the charges, and force is proportional to Q1 Q2 upon R square. Q1 Q2, that is the product of the two charges, R the distance between the two charges. Here F is equal to K Q1 Q2 upon R square. K is a constant of proportionality. Now constant of proportionality K, it is equal to 1 upon 4 pi epsilon. So that epsilon, it is epsilon naught, it is the permittivity of a free space. Epsilon, it is absolute permittivity. From that one, force is 1 upon 4 pi epsilon naught Q1 Q2 upon R square. F is equal to Q1 Q2 upon 4 pi epsilon naught R square. Now the vector form of Coulomb's law. Here the charge Q1, it is the charge Q2, here this one it is the origin, and the distance of that charge Q1 from the origin, it is R1, and the distance of charge Q2 from the origin is R2. Now the distances between the charges Q1 and Q2, that is a distance vector, that is R12. R12, it is a distance vector, and the direction of that vector, it is from the Q1 towards the Q2. Here the force exerted by Q1 on Q2 acts along the direction R12. Here A12 is the unit vector along R12, hence the force in the vector can be expressed as F2 is equal to Q1 Q2 upon 4 pi epsilon naught R12 square A12. Here A12 is unit vector, R12 is equal to, that is the vector magnitude of vectors. Here A12 is equal to R12 upon modulus of R12. R12 is R2 minus R1. Modulus of R12 is the distance between the two charges. The following observations are important. Here the force F1 is the force exerted on Q1 due to Q2. It can be written as in reverse, Q1 Q2 upon 4 pi epsilon naught R21 square A21. Q2 upon 4 pi epsilon naught R21 square R1 minus R2 upon modulus of R1 minus R2. But the R12 is equal to R1 minus R2 is equal to minus R2 minus R1, so that A2 1 is equal to A12. Hence Q1 Q2 upon 4 pi epsilon naught R21 square minus A21, it is equal to minus F2. The force due to the n number of point charges is equal to F on Q2 is Q1 Q upon 4 pi epsilon naught R1 Q square A1 Q. Because this is the origin, this is charge Q, that is Q1, charge Q2, charge Q3. The total force on charge Q due to the charge Q1, charge Q2, charge Q3. The charge Q, it is at a distance of R from the origin. The charge Q1, it is at a distance of R1 from the origin. The charge Q3, it is at a distance R3 from the origin, and the charge Q2, it is at a distance R2 from the origin. So that from that one, you will be writing F Q1 Q is equal to q1 q upon 4 pi epsilon naught. The R1Q square A1Q is equal to R minus R1 upon the modulus of R minus R1. So that similarly the force at charge Q2 due to Q is 4 pi epsilon naught R2Q square A2Q. So that A2Q it is the unit vector, and similarly the force exerted on due to Q3 on Q F Q3Q A3Q. So that FQ is equal to FQ1Q Q2Q Q3Q. So that the total force is Q upon 4 pi epsilon naught sigma is equal to 1 to n Qi, that is the charges R iq whole square R minus Ri upon modulus of R minus Ri. Any number of charges. I can take the any number of the integers values, so that it might be Q1, Q2, Q3, Q4, Q5, Q6. So that the total force exerted on charge Q due to the n number of charges. Here, shall consider the one of the example. A charge Q is equal to minus 20 microcoulomb is located at point 646, and a charge Q2 is equal to 50 microcoulomb is located at R 5,8 free space. Find the force exerted on Q2 by Q1 in vector form. The distance is given R in meters. From the coordinates of P and R, the respective position vectors are P is equal to minus 6ax plus 4ay plus 6az. R is equal to 5ax plus 8y minus 2az. So that the here find exerted on Q2 by Q1. On Q2 by Q1, Q2, 4 pi epsilon naught R12 square A12. Force is exerted on Q2 by the Q1. Here R12 is equal to RPR is equal to R minus P 11ax plus 4ay minus 8az. Modulus of R12 is equal to square root of 11 square plus 4 square minus 8 square. So that A12 is equal to R12 upon modulus of R12 11ax plus 4ay minus 8az. F2 is equal to 2, so that minus 0.0447 this values. So that this is the required force exerted on Q2 by Q1. The magnitude of the force is F2 is equal to square root of it is equal to 44.634 millinewtons. That is the force exerted on a charge Q2 by the charge Q1. Now, 4 point charges each of 10 microcoulomb are placed in free space at the points 1, 0, 0, minus 1, 0, 0, 1, 0, 0, minus 1, 0 respectively. Determine the force on a point charge of 30 microcoulomb located at a point 0, 1. Here the 4 charges are located along positive x-axis and negative x-axis at same distance from the origin, that is 1, 0, 0 and minus 1, 0, 0, that is positive x-axis, negative x-axis. Similarly, The other two charges are located along positive y-axis and negative y-axis. Positive y-axis it is 0, 1, 0, that is at the y is equal to 1, and the negative y-axis at the 0, minus 1, 0, that is the charge 4, it is on the negative y-axis. Now we have to determine the total force at a point which is on the z-axis 0, 0, 1. It is also at a same distance from the origin, that is on the positive z-axis 0, 0, 1. This is along negative x-axis, this is along positive x-axis, but here this is positive y-axis and this one it is negative y-axis. Here you have to determine the force on a point charge P which is at a distance of the at a point 0, 0, 1. Now the position vectors of the 4 points at which the charges q1 to q4 are located can be obtained as A is equal to Ax, because this is on positive x-axis, that is point A charge q1 is located. At point B, charge q2 is located. At point C, a charge q3 is located. At D, a charge q4 is located. So that the position vectors of that point A is equal to Ax, because y is 0 and z is 0. Position vector of point B is equal to minus Ax. Position vector of that point C, that is B, is minus Ax. B is equal to minus Ax and C is equal to, it is the plus Ay and D is equal to minus Ay. While position vector of point P, here charge 30 microcoulomb is situated, it is equal to Az. Consider force on Q due to Q1 alone is equal to Q1 upon 4 pi epsilon naught R1Q square A1Q. R1Q square to A1Q. Here Q1 upon 4 pi epsilon naught, here R1Q is equal to R1Q upon modulus of R1Q, that is a unit vector. R1Q is equal to P minus Az minus X and modulus of R1Q is equal to root 2. F1 is equal to, here Q is equal to 30 microcoulombs and Q1 is equal to 10 microcoulombs and 4 pi epsilon naught, that is 8.854 into 10 raised to minus 12 into, that is the distance, square root of root 2 square Az minus Ax upon root 2 Az minus Ax. So that modulus of R1Q is equal to R2Q is equal to R3Q, R4Q is equal to root 2. R2Q is equal to Az plus Ax. R3Q is equal to Az minus Ay, that is P minus C. R4Q is equal to P minus D is equal to Az plus Ay. A4Q is equal to Az plus Ay upon root 2. So that F2, F3, F4 is equal to QQ2, QQ3, QQ4. So that the total force F2, F3, F4 is equal to total force F1, F2, F3, F4 0.9533 Az minus X, Az plus X. Az minus Ay, Az plus Ay is equal to 3.813 Az. Okay. Now electric field intensity. Here, if any other F2, that is the, now consider a point charge Q1 as shown in the figure. If any other similar charge Q2 is brought near it, Q2 experiences force. In fact, if Q2 is moved around Q1, still Q2 experiences force as shown in the figure. So that if there exists a region around a charge in which it exerts a force on any other charge, this region where a particular charge exerts a force on any other charge located in that region is called electric field of that charge. The electric field of Q1 is shown in the figure. The force experienced by the charge Q2 due to Q1 is given by Ft is equal to Q2 upon 4 pi epsilon R12 square. Thus, the force per unit charge can be written as F2 is upon Q2, Q1 upon 4 pi epsilon R12 square A12. This force exerted per unit charge is called electric field intensity or the electric field strength. It is a vector quantity and is directed along a segment from the charge Q1 to the position of any other charge. It is denoted by E, so that E is equal to Q1 upon 4 pi epsilon naught R1 P square E1. Here P is position of any other charge around Q1. E is equal to Q1 upon 4 pi epsilon naught R square AR, because here if Q2 is equal to 1 Coulomb is considered placed at a distance r from the origin, then the force acting on Q2 due to Q1 is along the unit vector AR. As the charge Q2 is unit charge, the force exerted on Q2 is nothing but electric field intensity E of Q1 at the point where unit charge is placed. So that due to which in general we shall be writing that is Q1 upon 4 pi epsilon naught R square AR. Q1 is located at the center of a spherical coordinate system, then the vector ER in the equation 3 becomes the radial unit vector ER. Radially outwards, E is equal to Q1 upon 4 pi epsilon naught R square ER in spherical systems. In spherical coordinate system, it can be written here in these forms. In cylindrical, in the Cartesian, we shall write that is Q1 upon 4 pi epsilon naught R square ER. The definition of electric field intensity E is equal to force per unit charge, force measured in newtons and charge is measured in coulombs. So that here electric field intensity, it can be measured, unit of that is newtons per coulombs. Here the electric potential has units joules per coulomb, and hence E is also measured in terms of volts per meters. This unit is practically to express E. Methods of obtaining E in Cartesian coordinate systems. E due to the n number of charges, here the point P it is present. Here electric field at a point P due to charge Q1, electric field at a point P due to charge Q2, electric field at a point P due to Q3, Q4 and Q1. So that here the total electric at point P is the vector sum of the individual electric intensities produced by the various charges at the point P. E is equal to E1 plus E2 plus E3 plus dash En. R1 square, R2 square, Rn square. Q1 upon 4 pi epsilon naught R1 square AR1, AR1 and AR2, and the Qn upon 4 pi epsilon naught Rn square, so that ARn. E is equal to 1 upon 4 pi epsilon naught square sigma I is equal to 1 to n Qi upon Ri square ARi. Here the each unit vector can be obtained by using the method discussed earlier, so that here ARI is equal to RP minus RI upon RP minus RI. RP is equal to position vector of point P, and the RI position vector of point where charge Qi is placed. Calculate the field intensity at a point 3, 4, 5 due to a charge of 5 nanocoulomb placed at 1, 2, 3. Here a charge A is placed at the 1, 2, 3, and here B is placed at 3, 4, 5 due to a charge of 5 nanocoulomb placed at the charge A. It is placed at 1, 2, 3, that is point A, and the B it is 3, 4, 5. At that point we have to determine the electric field intensity. The position vectors of A and B are RA is equal to AX plus 2AY plus 3AZ, RB is 3x plus 4ay plus 5az, RAB is equal to B minus A 2ax plus 2ay plus 2az. Here is equal to RAB upon modulus of RAB is equal to B minus A upon modulus of B minus A. E is equal to Q upon 4 pi epsilon naught R square AR. Here 2x plus 2ay 2az upon 3.46 is equal to this values. So that Q upon 4 pi epsilon naught R square AR, here this one you will be getting the equation as the AR is this values, and from that one you will be getting the electric field intensity. Value of this electric field intensity is equal to these values, because ER it is already calculated 0.5773 into bracket of AX plus AY plus AZ. Okay. Now the types of charge distributions. Here point charge. That is the corresponding. It is seen that if the dimensions of a surface carrying charge are very small compared to region surrounding it, then the surface can be treated to be a point. The corresponding charge is called a point charge. The charge may be spreading along a line, that is a line charge. Total charge in coulombs and total length in meters, that is line charge. And surface charge. If the charge is distributed uniformly over a two-dimensional surface, then it is called a surface charge or a sheet of charge. Volume charge. If the charge is distributed uniformly in a volume, then it is called the volume charge distribution. Here it is a cylinder is there, here it is a cube is there, so that the total charge in coulomb upon total volume in cubic meters. Total charge in coulomb upon total volume in cubic meters, that is the volume charge density. The volume charge density is denoted as rho V and is defined as the charge per the unit charge per unit volume. So the total charge in coulomb upon total volume in cubic meters. Okay. Surface charge. Surface charge, it is the total charge in coulombs upon total area in square meters. Total charge in coulombs, total area in square meters, that is coulomb per meter square. Thus rho s, it is expressed in coulomb per meter square. That is surface charge density is expressed in terms of coulomb per meter square, that is total charge in coulombs, total area in square meters. Here it is in for volume charge density, it is total volume in cubic meters. Similarly, the line charge density, the charge density of the line charge is denoted as rho L and defined as the total charge in coulombs upon total length in meters, that is coulomb per meters. Line charge density is total charge in coulombs upon total length in meters, that is coulomb per meters. Okay. Here now we shall determine the one of the problem on the how to determine the electric field intensities due to the all the three charge distributions. First one, that is for the electric field due to the line charge distributions. First is some differential element is considered along the line. On the differential length dl is considered, that is dq is equal to rho l dl. That is rho l, it is line charge density. It is the dl, it is the differential length of the element. This is total line charge. So that the differential charge, that is the small charge which is located in that differential length, it is differential charge. So that the differential electric field d is equal to dq upon 4 pi epsilon naught r square er dl upon the dq is equal to rho l dl 4 pi epsilon r square er. So that the electric field, total electric field E at a point P due to the entire line charge can be obtained by integrating this equation. So that E is equal to integral L, that is the total length of line charge 4 pi epsilon r square. E due to surface charge. Here also a small differential surface element is considered on the surface of a surface having a charge density rho s. Now the charge dq on the differential surface area ds is equal to dq rho s ds. Hence the differential electric field d at a point P, it is equal to d is equal to dq upon 4 pi epsilon r square er. dq is equal to rho s ds because a small differential this is the total surface. This is the total surface. On that total surface, a small differential element is considered, that is having the area, it is equal to ds. And the area of that small differential element is on the surface is equal to ds, and the charge which is located in the differential surface element is also equal to dq. From that one, the differential electric field intensity at a point due to that differential surface element on the surface is considered dq is equal to 4 pi epsilon r square er. Here dq is equal to rho s ds. Hence the total electric field E at a point P is to be obtained by integrating the differential electric field D over the surface area on which charge is distributed. So that total electric field is equal to integral rho s ds upon 4 pi epsilon r square er. Similarly, E due to volume charge density. Consider a volume charge distribution having a charge density rho v, that is the volume charge distributions. So that the differential, if we consider the charge dq on the differential volume, here this is the total volume, and this one it is the differential volume which is considered within that the large volume. That the differential charge which is present in that differential volume element is equal to rho v dv. Hence the differential electric field can be dq upon 4 pi epsilon r square er rho v dv upon 4 pi. Total electric field it is obtained as interior volume rho v 4 pi epsilon r square er. So that thus if there are all possible types of charge distributions, then the total electric field at a point is the vector sum of individual electric field intensities produced by each of the charges at a point under considerations. If all the charges are all charge distributions are present in a medium, that is point charge, line charge, the surface charge and volume charge, then the total, if want to determine the electric field intensity at a point due to all the four charge distributions, point charge, line charge, surface charge and volume charge, so that it is equal to this values. Now the electric field due to a infinite line charge. To determine the electric field at a point due to the infinite line charge, that is the line charge, it is distributed from minus infinity to plus infinity. Field due to the infinite line charge. Here also, because directly it's not possible to determine the electric field at a point due to an infinite line charge distributions, because the length of the line it is from minus infinity to plus infinity and charges are distributed along that line. The uniform charges are distributed along the line, so that it is not possible to determine the electric field intensity at a point due to that one. For that one, you have to consider the small differential element along the length of the infinite line charge, which is distributed along the z axis, that is minus z to plus z, that is minus infinity to plus infinity. Now that the charge which is present in the differential element is equal to rho l dl l, because this one it is the length of that differential element and rho l it is the line charge density, so that rho l into dz, because since that infinite charge is placed along the z axis, so that here you have considered that is dz. The coordinates of the differential charge element are 0, 0, z, while the coordinates of point P, here you have to determine the field intensity are 0, r, 0, because hence the distance vector can be written. That is here the point P at which you have to determine the electric field, and the differential element which is considered on the infinite charge, it is at this point, that is dl, and here it is dq. So that here the distance vector r can be r from the dq to p is equal to rp minus rdl, because that is the differential length of the element which is considered along the line. The coordinates of the point P, the coordinates of this point P, it is equal to, it is at a distance of r from the line charge. This point P, it is at a distance of small r from the infinite line charge, so that the coordinates of that point P are the coordinates of that point P are 0, r, 0, because it is along the y-axis, so that the 0 comma r comma 0, and the coordinates of that differential charge equal to 0 comma 0 comma z. From that r ay minus z az, because coordinates of point P are 0 comma r comma 0, and the coordinates of that differential charge it is equal to the 0 comma 0 comma z, so that here the distance vector from that differential charge to the point P is equal to r ay minus z az. From that the modulus of r is equal to square root of r square plus z square. Here the unit vector in that direction from the differential charge to the point P is equal to r upon modulus of r ay minus z az upon square root of r square plus z square. D is equal to 4 pi epsilon naught r square. Here this is the formula which is used to determine the electric field intensity at a point due to any of the charge distributions. So that since it is line charge distribution, so rho L into dz, because here it is the placed along the z axis, that's why here it is considered dz 4 pi epsilon naught, and r is square root of r square plus z square, and unit vector is r ay minus z dz square root of r square plus z square. Now here for every charge on positive z axis there is equal charge present on the negative z axis. Hence the z component of electric field intensity produced by such charges at a point P will be cancel each other. Hence effectively there will not be any z component of E at a point P. This is shown in the figure. Hence the equation of dE can be written by eliminating a z component. Here az r ay minus z az, because the line charge it is distributed uniformly along the negative z axis and the positive z axis, so that the electric field intensity due to this z component at the point P due to the z components it will be cancels each other, because equal distribution of that line charge along the negative z axis and along the positive z axis, so that the that z component is cancels in the calculation of that electric field intensity. So that here it is the terms, that is here it is the positive z axis and here it is the negative z axis, so that the total electric field intensity at a point P due to the z component is cancels. That's why you shall eliminate that z component in the equation for the electric field, so that now it will reduces to rho L dz upon 4 pi epsilon naught square root of r square plus z square whole square r ay square root of r square plus z square. Now by integrating dE over the z axis from minus infinity to plus infinity, we can obtain the electric fields. E is equal to integral, because it is extending from minus infinity to plus infinity, rho L upon 4 pi epsilon naught square plus z square whole raised to 3 by 2, because here it is 1 by 2 plus here it is the square root of r square plus z square, it is equal to the r square plus z square, plus here it is square root of r square plus z square. Now both of these, here r square plus z square, here r square plus z square whole raised to 1 by 2, so that these two it will results into r square plus z square whole raised to 3 by 2 r dz ay. For such an integration, use the substitution z is equal to r tan theta, that is the r is equal to z upon r tan theta. How you have got that this equation? Because here Here in this example, the differential charge from the origin, it is at a distance of z from the origin, and the differential charge, the point P from the line charge, it is at a distance r from the origins, and it is an infinite line from extending from minus infinity to plus infinity. So that here if some angle theta is considered and it is forms a right angled triangle, from that one tan theta is equal to z upon r, opposite by adjacent, opposite side by adjacent side. Here if we consider at this point an angle theta, so that here z is equal to r tan theta, that is z, therefore r is equal to z upon tan theta, and if a differentiation is taken, dz is equal to r, the differentiation of tan theta is equal to sec square theta d theta dz. Here r is not a variable of integrations, because r is constant, it is at a the point P, it is at a distance, constant distance r from the origins. Now for z is equal to minus infinity, theta limits of integrations. The tan inverse of minus infinity is equal to minus pi by 2 minus 90 degree, and z is equal to plus infinity, theta is equal to tan inverse of plus infinity is equal to pi by 2, so that it is equal to plus 90 degree. Now therefore the electric field intensity is equal to, now the limits of integrations will change, that is theta is equal to minus pi by 2 to plus pi by 2 rho L 4 pi epsilon naught. Now r square plus r square tan square theta whole raised to 3 by 2 into r into dz, because rho L r dz ay, rho L r into dz is r sec square theta d theta ay. Rho L upon 4 pi epsilon naught integral minus pi by 2 to plus pi by 2 r square sec square theta d theta upon r cube into bracket of 1 plus tan square theta whole raised to 3 by 2 ay. But 1 plus tan square theta is equal to sec square theta. The electric field is equal to rho L upon 4 pi epsilon naught integral minus pi by 2 to plus pi by 2 sec square theta d theta upon r sec square theta sec cube theta into ay. Rho L upon 4 pi epsilon naught to r integral minus pi by 2 to plus pi by 2 cos theta d theta ay. Sec theta is equal to 1 upon cos theta, because here the 1 plus tan square theta is 1 plus tan square theta is equal to sec square theta. Sec square theta whole raised to 3 by 2 is sec cube theta, and here sec square theta is present and here sec cube theta is present, so that it is equal to cos theta. Now rho L upon 4 pi epsilon naught r to the integration of cos theta is sin theta, integral of minus pi by 2 to plus pi by 2, those are limits of integrations. Sin pi by 2 minus sin pi by 2 is equal to rho L upon 4 pi epsilon naught, rho L upon 4 pi epsilon naught into 2 ay, 2 pi epsilon naught r ay volt per meters. That is the electric field intensity at a point due to an infinite line charge. So that here rho L, it is the magnitude of the line charge, and r, it is the distance of point P from that line charge. R is perpendicular distance of point P from the line charge, and here a unit vector in the direction of the perpendicular distance of the point P from the line charge. So that this is the electric field intensity at a point due to an infinite line charge. It depends upon the magnitude of the line charge, and it is distance magnitude of the line charge, and it also depends upon the distance of the point P from that line charge, and a unit vector in the direction from the line charge to the point P.